Shakeel from Charles Darwin University, and he's presenting the study of organic light emitting diodes on optimum light emission efficiency.
Good evening, everyone. My name is Usman Shakeel. I'm a final semester student of Bachelor of Electrical and Electronics Engineering from Charles Darwin University. As a requirement of my degree, I had to do a project, and the topic of my project is study of organic light emitting diodes for optimum light emission efficiency. My supervisor for this topic is Professor Chase. So, as the time has passed on, our reliance on general lighting has increased considerably. No matter whether it's an electronic device, which we would like to use before going to the bed, or a general lighting device. It seems like lighting has become an essential part of our life. Just for a moment, imagine this room without any lighting device. Not even this light, not those lights. How it would be? Dark? Might be very dark. So there is a need to look up for more efficient and sustainable lighting devices. And this is where organic light emitting diodes come into play. They're very efficient, reliable, and sustainable. So what is an organic light emitting diode? It is a light emitting diode in which the emissive and conductive layers are composed of organic compounds. As you can see here in the figure, the emissive and conductive layers, which are sandwiched between cathode and anode, are composed of organic compounds. An organic light emitting diode emits light in response to an electric current and usually requires a very low voltage between 2 to 10 volts. So there are so many other lighting devices. Why particularly organic light emitting devices? Firstly, they're cheap. Secondly, they're thin. As they're thin, so they're flexible as well. They produce bright light constituting of vibrant colors. They can be transparent as well. And most importantly, they do not require backlight as compared to their counterpart LEDs. So they can produce true black colors without any need of electricity. The working principle of an OLED is very simple. Firstly, electron and holes are injected through cathode and anode respectively. Then due to the strong electrostatic forces in organic semiconductors, these electron and holes are attracted towards each other and they form an electron-hole pair, which is also known as an exciton. In the third step, this exciton can be combined radiatively in the emissive layer, and finally, the light is emitted. So when an exciton is formed in the emissive layer, this is where the main issue with the OLEDs is. Only the singlet exciton can be combined radiatively. So when an electron and hole is injected through cathode and anode respectively, and it combines in the emissive layer, then if the spin of that electron-hole pair is antisymmetric, as shown here in the figure, then that exciton can recombine radiatively, emitting light. There is only one possible combination of singlet exciton in OLED, which is shown here. The second case is when a triplet exciton is produced. So when electron and holes are injected through cathode and anode, and they combine in the emissive layer, then if the spin of that electron-hole pair is symmetric, then such an exciton is triplet exciton. This exciton cannot recombine radiatively, and this is forbidden in OLEDs. There are three possible combinations of triplet excitons in OLEDs, which are shown here at the bottom. So, the ratio of singlet to triplet excitons in an OLED is 1:3, which means that 25% of the excitons produced in an OLED are singlet, while 75% of them are triplet. Hence, the internal quantum efficiency is restricted to around 5% only. So there is a need to enhance the light emission efficiency of OLEDs so that the triplet excitons can also be utilized and the light emission efficiency of OLEDs can be increased. And there are different methods to do that. The first one is using fluorescence-based OLEDs. In these OLEDs, the internal and external quantum efficiency of OLEDs is still very low, so they're not used. The second one is using phosphorescence-based OLEDs. These OLEDs can realize 100% internal quantum efficiency. But there is a catch. They require doping with heavy metals like iron. And as I said earlier, that there is a need to look up for sustainable devices. So these devices definitely do not fit the requirement for that in future. The third method is using TADF-based OLEDs. These OLEDs can also realize 100% internal quantum efficiency. And they also do not require doping with heavy metals. So they are very sustainable as well. But one thing should be noted here, these OLEDs are not available in the market yet. This technology is only limited to one group in the world, which is based in Japan, Diode. So keeping all this information in mind, the main objectives of my project were to understand the operational principle of TADF-based OLEDs, then find a method to enhance the lifetime of OLEDs. The operational instability is one of the main issues with OLEDs. And the third was to find the light emission efficiency and compare the results with the experimental work. So firstly, the concept of TADF-based OLEDs. In TADF-based OLEDs, there is a small energy gap between singlet and triplet excited state, as shown here in the figure. It is usually 0.5 to 1 electron volt, but it could be very less than that as well. Then due to this small energy gap, the triplet excitons are converted back to the singlet excited state at room temperature, and they can recombine radiatively, hence 100% internal quantum efficiency is realized. There are two key parameters which are required for the triplet to be converted back to singlet excited state. The first one is strong exciton spin orbit interaction. Due to the small energy gap between singlet and triplet excited state, the first order mixing coefficient between singlet and triplet excited state is very high, and hence the exciton spin in orbit interaction is very high, and the spin of the triplet exciton is flipped. After that, due to the molecular vibrational energy overlap, these triplet excitons whose spin has been flipped can be converted back to singlet excited state, and then they recombine radiatively, making light. The second, lifetime. So recently, Adachi and his co-workers, they conducted some experiments, and they found out that the lifetime of TADF-based OLEDs can be enhanced significantly by using ultra-thin interlayers of 8-hydroxy-quinovolate lithium, which is referred as LIQ as well. These interlayers can be placed at different places in an OLED, but they found out that by placing these layers between emissive and conductive layers, the lifetime of TADF-based OLEDs can be enhanced by 8-fold. The results obtained are shown here. And as you can see, compared to the reference device, the lifetime of TADF-based OLED has increased by 8-fold. Similarly, for another device, the lifetime increased by 16-fold. The LT90 is the lifetime to reach 90% of initial luminance. Finally, the most exciting part of this project, calculating the light emission efficiency. So to calculate the light emission efficiency, 4 parameters are required. The first one is intersystem crossing, which is the rate of singlets being converted to triplet excited state. Second is reverse intersystem crossing, which is the rate of triplets being converted back to singlet excited state. The third is rate of prompt fluorescence, which is the rate of light emission from singlet excitons. And fourth is rate of delayed fluorescence, which is the rate of light emission from triplet excitons being converted back to singlet excited state. Firstly, I calculated the rate of intersystem crossing by using the expression derived by my supervisor very recently, and compared the results with experimental work as shown in the last column. The results are very reasonable. Secondly, I calculated the rate of reverse intersystem crossing. For this, I had to incorporate my supervisor work with Adachi's work. And I obtained a new equation, and then I calculated the rate of reverse intersystem crossing and compared the results with experimental work. Again, they were in reasonable agreement. After that, I calculated the rate of prompt fluorescence by the equation derived by Singh. Usually this is in 10 raised to power 9 per second. And then I calculated the rate of delay fluorescence. For this, again, I had to incorporate this work with Adachi's work. Finally, I calculated the internal quantum efficiency of TADF-based OLEDs by using their general equation. And then using that, I calculated the external quantum efficiency by multiplying it with the outcoupling efficiency, which is between 20 to 30% for TADF-based OLEDs. The final results for different organic materials have been shown here in the last 2 columns, and they are very reasonable. So what's on from here? The theoretical external quantum efficiency of TADF-based OLEDs has been calculated for the first time. This is, I believe, so to the best of my knowledge. There is reasonable agreement between theoretical and experimental results. And as it is so these equations can be used to calculate the maximum theoretical external quantum efficiency, and then that method can be used to obtain highly efficient TADF-based OLEDs in future. So these results are expected to provide a pathway to manufacture highly efficient TADF-based OLEDs in future. In the end, I would like to thank you all for your time and patience, and any questions, please.
Questions from the judges? Okay, so how long have you been working on this development? It's pretty intriguing how you got together.
Yeah, this is about 6 months, 2 semesters. Yeah.
And
Technically,
success, how it sort of eventuated into tech?
I was actually very obsessed with the Organic Light Emitting Diodes at first, so I started working with him, and then we found out that this is very new research, that TADF-based OLEDs have not been introduced in the market yet. They're going to be introduced in the market by the end of this year or by the start of next year. But there was a need for that because look at your phones, like iPhone or Samsung or organic light emitting TVs. They're very expensive, like $5,000, or maybe your phone, the next iPhone is about $1,600. And the OLED screen almost costs like $150 for that phone. So there was a need to find some sustainable and reliable and cheap lighting devices, and this is where we ended up.
Any further questions from the judges? The questions is open for the floor. If anyone has questions from the audience. Well, thank you very much for all the
Thank you.